we talk about this trend in the industry with more and more of the responsibilities being placed onto the design engineers and PCB designers, and that's what I say, with the rise of the all-purpose engineer, this next speaker very much continues that theme. So the gentleman I'm about to bring up is really very much what I would say is an engineer's engineer. He sees problems in the world, and seemingly those problems tend to be things that he's interested in already, and he comes up with solutions to solve those problems. Likewise, the title of his talk today is Becoming a Full Stack Engineer. I like that very much. Yes, it's a software term, but we're seeing more and more of that, not just the responsibility for the design, supply chain, I should say, but also the manufacturing, but also now the embedded development and the software elements of the designs are really being more sort of consolidated at the engineer's desk. So with that, I won't waste any more of your time. We'll just bring up Eli Hughes. Thank you so much.
Eli Hughes is the CTO of T0 Research and Development, which develops ultrasonic acoustic sensors and software for the craft beer, glycol chilling, and synthetic biology industries. In addition to his current role at T0, he also does work for NXP Semiconductors and helps develop software and electronics for the pyrotechnics industry. His technical background is in electronics, embedded systems, software, and acoustics. In a previous life, he worked at the Penn State Applied Research Lab, where he was doing research in the areas of sensors, condition-based maintenance, robotics, undersea vehicles, and space science. Eli also taught courses in embedded systems, FPGAs, and circuit theory at the Penn State University EE department. In his spare time, he plays the guitar and keyboard in addition to enjoying woodworking. Please welcome Eli Hughes.
Hello, and welcome to Altium Live 2020. I'll be your host for this presentation. My name is Eli Hughes. I'm the CTO of T0 Research and Development. And today, we're going to talk about becoming a full stack hardware engineer and all the chasms that you may need to cross to be able to get there. So along the way, we're going to look at a connected product dealing with the craft brew industry. It's kind of neat, so if you want, crack open a cold one and let's dive in. So first, we're going to talk about some goals. Goals are important. First goal is I want to validate some of the experiences you may have had along your career while offering some of my experiences and my path, because everyone's path is just a little bit different, and it's nice to see other people's experiences. I also want to try to engage your hardware engineering interest through storytelling. I also want to communicate not only some engineering details, but another important factor in engineering are the human factors. So some non-goals, I'm not really here to present super highly technical information. Some of the information, there will be some equations, but it's not going to be super technical. And I'm not here just to read the slides. This presentation is not necessarily standalone. I want to talk and tell a story so we can have some fun. Now, specifically, we're going to divide this up into 4 sections. We're going to talk a little bit about myself and my path and how I got here today. Once again, I think seeing other people's paths in life is really helpful because you can gain some perspective in your own hardware engineering skills by seeing how someone else did it. It's smart. I do want to talk about a challenge in engineering, especially today, as there's such a wide dynamic range, of information, technologies, and tools that you need to learn to become, of what I consider a good full stack hardware engineer. Anyone can do this, and anyone who wants to can do it, but it can be somewhat overwhelming. So we're going to take a look at this kind of dynamic range problem. In the midst of that, we're going to talk about a connected product that T0 has developed for the craft brew industry for monitoring fermentation in beer, the synthetic biology industry for looking at how yeast ferment to create new products, as well as applications in like HVAC and monitoring fluids and glycol. And it's kind of a neat product because everyone likes beer. And lastly, I think it's important to really be a complete round engineer is talk about some of the human factors. Some of the human factors can be real impediments to becoming a truly great engineer. So I think it's really important to discuss. Now, where do we begin? So I thought about this and I thought, well, let me tell my story. Every story is a beginning. We were all born somewhere and we all grew up somewhere. So I grew up in Ludlow, Pennsylvania, on an old farm. You can look at the dot there. Ludlow is a village of 300 people. Nearest neighbor is probably, 1,000 meters away. Had to go several miles over the hill to see other people. But a lot of times I tell people I'm from Kane, Pennsylvania. A lot of people know where Kane. It's the black cherry lumber capital of the world. And best access to the Allegheny National Forest. And the reason I'm telling you this is that anyone can get to where they want to. It doesn't matter if you're from small town, big town, small city, large city, poor, rich. You can get to where you want. Now, I think my upbringing had certainly, as from this story, an influence of how I developed as an engineer. And being in that old farmhouse actually did mold and shape who I was, and it affects my decision-making process to date. And I think it's important to understand the things that factor into how you make decisions, because that's how you become an engineer. So my introduction to electronics and computing, everyone has the thing. My thing was the Nintendo Entertainment System. So I believe the NES was released in the US in 1985. Around that time, we had an arcade in the back of a gas station in Kane, and I loved the arcade games. There was Super Mario Brothers on the arcade platform. Loved the game, loved playing it. Played another game called Gauntlet. Spent many of my father's quarters in that game. But when the NES was released, it was a big deal for me because it brought some of that arcade experience home. And a lot of people, a lot of Gen Xers coming through the 80s have fond memories of the Nintendo. And I say this is my introduction to electronics and computing because it was a computer. It was my real first exposure to a lot of game time, a lot of time in front of Legend of Zelda, Excitebike, Mario Brothers, Metroid, Punch-Out. And why this is important. I think video games, for me, really was my first introduction to really thinking about how things work, because while I enjoyed the games, you start to wonder, how does this thing work? How can it move that sprite across the screen? How can it make these sounds? How does it interact via the controller? Because I wanted to know that because I wanted to make a game. I thought, boy, I had some ideas of my own. I would love to make my own game. So enter year 1990. So for me, 1990 was the 7th grade. I was a little ahead in school, so I was a little young for 7th grade, but we had a course called computer literacy. The first day of computer literacy, 7th grade, is an awkward time for everybody. You're just turning into an adolescent. You're coming out of being, elementary school. You're coming halfway through middle school. Everyone's weird. Emotions are weird. And one day I walk into this classroom with these beige boxes, the Apple IIe computer. So for me, that was my real first exposure to a computer. Growing up on the farm, like I said, my first computer was really that NES, Nintendo Entertainment System, but there was a key difference with this device. That key difference is you could program it. Now, in computer literacy is split up half and half. The first half was learning how to use the computer. So there were programs at the time for spreadsheets. There was basic database, learning how to print We printed on dot matrix printers, these really large, banners, and it was a lot of fun. So the next part was programming. Now, for anyone who was familiar with the Apple II at the time, the Apple II came loaded with Apple Basic. Now, we spent half the year on Apple Basic, and we started with typing programs that were, printed off on the roll-off machine, the duplicate machine. And we had this classic blue paper we would look at and just transcribe programs. And for me, this was a source of real empowerment. And you might think, why would a funky little seventh grader who's kind of weird feel empowered? Because you could write code. I could write a simple program and generate some sort of I/O. That to me was extremely powerful. And what made it even more powerful was that after we practiced transcribing programs, we had to read some of the manuals. And there was a graphics programming manual. And at some point, reading through there, you get to a part where you learn how to do basic things like draw lines. And as soon as this happened, the first little thing clicked in my brain. And it was like, wait a minute, I can draw lines. I can put lines together horizontally and vertically. I can turn on pixels. I can make that Nintendo game. And that's why I say that was empowering. That for the first time, I had something else I was interested in, and I had some control of the results. So at that point, I was hooked. I couldn't get enough. We couldn't afford the Apple IIe, so I got as much as I could at school trying the program. And it was a really exciting time. And I really remember how excited I was just to be able to dig in. Now, in 7th grade, of course, you're hanging out with your friends. We had a lot of all-night parties playing the NES and, doing all the things 7th graders do. But one of the sources of casual reading at the time was Nintendo Power. It was a big deal. We got it in the mail. You could read through, see gameplay, footage, playing through a game. You get questions and answers. And the other thing that was interesting, what we had in that computer lab was an actual technical reference manual. So computers at the time actually came with a manual that had schematics and a lot of low-level information that you don't necessarily get these days. Now, the reason I bring this up, because I had both sources of information here, and I was spending time in both, and there was one issue of the Nintendo Power. I would reread that magazine over and over again. It was, what a source of entertainment. But at some point, it mentioned some of the technical specifications of the NES. Well, lo and behold, the first dot that got connected, I read some of the tech specs for the NES. At the same time, I was reading through the technical reference manual for the Apple IIe, and the first big dot got connected. The venerable MOS Technology 6502 microprocessor. A lot of people cut their teeth on this processor, and for me, this was such a huge click between these two things, because I kind of figured, okay, this chip is in both of these things. I really didn't understand all the ins and outs, but there was a 6502. Nintendo said it was in their machine, as well as Apple said it was powering theirs. So there was a connection, and connection is really important in learning. And so for me, there was a new equivalency in my life. That even though these boxes, kind of beige boxes, were different, they really, in my brain, they were the same. Because they had the same thing making them work. It's like taking apart a car, and all cars have a motor. The motors might be a little different, they might be connected a little different, but they have a motor. And this was huge. And at that point, I got super hooked and super pumped that a little bit of the magic was unveiled to me at that age. And I wish everyone could experience how awesome that is, to make a connection like that, because it truly is exciting. Now, the first thing that I ran into after doing the graphics programming and playing around, there were some examples of how you do basic operations. One thing that I could immediately notice is anything I did on that Apple computer was slow. It was tortoise slow. While the NES could do a lot more. It could draw a lot more colors. It can move a lot more things on the screen. And I worked really hard to try to figure out why was that. And at the time, the teacher knew enough to teach the basics about the computer, but the instructor wasn't necessarily an expert at it. So I really wanted to know why. Until looking in the manual, spending some time reading with some more magic. And this was super magic. Peek, poke, and call. And when I first saw peek and poke, I had a really hard time getting around it. And they used the terms assembly language. But while I didn't understand how it worked at the time, I could understand the implications of using it. Because there were certain peek, pokes, and call that could do things like render sprites really quick without flickering on the screen. I could get a lot more done. And that was the very first next connection into a world that I would never escape, is entering assembly language, because it enabled me to take the next step. This was the tool of the wizards at the time. This is how you got what you wanted out of the machine, because you were programming closer to what the machine, how the machine works. And for me, once again, in 7th grade, it started out as magic, but it quickly turned out that it wasn't magic, that you could read about this stuff, get information, and be empowered by being able to program it. Now, moving on, I want to tell another little story. So I did have a good time with the Apple IIe. I was out with my mother. My mother lived in Pittsburgh at the time. And on the weekends, she would like to go out on her time off, and we would go to flea markets. Now, the only thing I wanted to do was stay home and play my NES. I wanted to play games. I hated going shopping. I mean, I was probably a horrible child having to be drugged through these flea markets. But lo and behold, one flea market that we were walking through, mostly focused on books, I was bored out of my gourd. I could not stand it. But just looking around, something caught my eye. Was this text. Programming the 6502 by Rodney Zacks. Looking through this book, it had what I needed. It had, all of the opcodes. I knew when I saw this was the piece I needed to take the next step. And for me, it's like lights shine down from the heavens and a gift was delivered. And I had to beg my mom, because my mother didn't really understand what this book was about. But I knew I needed it, and I convinced her, I got to have this book, because now what I could do is go home in the evenings, write out programs to enter them into the Apple II, the assembler that you could go and enter programs. And I could really speed up what I was doing. And it was such an awesome experience. And it seemed like all of these things coalesced just at the right moment, to capture my interest. Now, over the years, like I said, the 6502, a lot of people cut their teeth in the 80s on this processor. I mean, it was inexpensive, it was easy to program, it was plentiful. And I feel really lucky that coming up in a time, because in some ways processor architectures are much simpler. While they share a lot of the same heritage and they work in similar ways, starting off with something like the 6502 was a great entry into the world of computing. And the reason I bring up the Terminator, right, another great 80s movie, but one thing you might not have known is when the Terminator kind of turns on and he goes back in time and is looking around in his heads-up display, there's all kinds of opcodes coming up through the screen. Well, if you take some time to look at it, those are 6502 opcodes. In instructions. So it was everywhere. And there's a lot of places you can find 6502, and I just love every time I see Terminator that those fly on the screen. It just brings back such a great memory. Now, year will move forward to 1992, starting high school, different building. Unfortunately for me, there were no computer programming classes. There were classes in typing and a little about using the computer for things like photo or basic digital drawing and whatnot. Photo editing wasn't really a thing with the Macs, but we didn't. There was no exposure to any more programming, and for me, this was really disheartening because I really liked the coding aspect. So I lost all interest. Some of the really important classes, algebra, which forms the basis of a lot of computer science, chemistry and physics, which formed the basis of a lot of engineering, I did poorly because I just didn't care. And I think a lot of young people fall into this trap, and even people of any age, that you lose motivation, you lose purpose. In getting purpose into your life in engineering is, I think, really important. It makes you a better engineer. So for me, the grades went down the tubes for those classes. But I did have a personality, and I still do, somewhat obsessive, that I discovered music. My father had played in bands, since the time I was a baby. He was a drummer. I was always exposed to music. I hadn't really been interested up until then, but I really got into playing keyboard. I discovered that I really liked the keyboard. It was just like another machine to program. And one of the first real instruments that I managed to get my hands on was the Ensoniq SQ2. So the SQ2 was a performance synthesizer, really powerful machine. It had a sequencer. You could record tracks. At the time, it sounded phenomenal. Ensoniq was from Malvern, Pennsylvania, kind of a local company, and they were considered the best of the best at the time. And then as I marched on through high school, I really got into playing guitar. I loved the guitar. I loved like 80s hair band, and then in the 90s, grunge rock was was my thing. So I really loved, guitar rock and, grunge rock. So a different path. I thought I wanted to go to music school, but it turns out my dad really convinced me that if you don't know what you want to do, you think you want engineering, check out electronics. To me, I wasn't super into electronics per se. I knew that was what powered the computer. I really liked programming. But I decided to visit the Pennsylvania College of Technology. And when I saw the program, that the people in electronics, they were programming computers. They were writing at the time x86 assembly language to program things on a breadboard and to automate different pieces. They were controlling robots, and they were interacting with the world. And that was such a big deal to me, that my code that I could write could affect the world around me. And it was just such another eye-opener. So starting in 1996, I went to Penn College in Williamsport, Pennsylvania. It's a tech school. It was a 4-year program. You still have to do calculus and differential equations, just like an engineering program, but there's a ton more labs. And we started off with digital electronics, op-amps, transistors in the first year. And that's different than most engineering programs. Well, once I found a new purpose, I discovered that I really loved this. I loved the idea of the empowering nature of writing code, and I can control something in the external world. I just didn't have the piece of the electronics of how to do that. Well, once I had this new mountain to climb, I found some purpose. Calculus, I became interested. I saw a definite need for the calculus, differential equations. I'm not going to say I liked it at all times and it was easy, but those courses certainly became easier for me, that I had purpose. And electronics was extraordinarily enjoyable for me. And I look back at that time as a really good time. Now, as an aside, where I started circuit board design, in your third year at Penn College, they had a course in circuit board design and prototyping. So we learned how to use Protel, and I remember we started with version 2.5. Came on floppy disks. I believe we ran it on Windows 3.1 at the time. And maybe we upgraded the Windows 95 at some point. It was a great course because we etched our own PCBs. At the time, we didn't have the low-cost PCB service that we could send away boards for dollars and get them back. that existed only if you had hundreds of dollars or thousands of dollars. But I look back and laugh because there's things I see in ProTel that still kind of exist, and it makes me chuckle a little bit. And I spent a long time etching boards on my own time. I just thought, boy, what a neat way to prototype more complicated things. And so that's where we learned ProTel, and that was kind of my introduction of what would become Altium. Now, college, as I learned more and more, it gave me the opportunity to unlock things in my life, because 1996, the internet was certainly available to certain people. Growing up in my hometown, a handful of people had something that they could dial into, nothing like the internet of today. And I really didn't get an opportunity to get on the web until I went to college. We had a computer lab, and holy cow, I saw, well, everyone else saw chat rooms and GeoCities and AngelFire websites, which I certainly partook in my share, that I can now look things up and I can unlock things. Now, the synthesizer here that I'm going to talk about, the SQ2, I did a lot with that. Now, the neat part about unlocking things is I can make other discoveries. Taking that thing apart was the Motorola MC68000. And Penn College at the time taught a lot in the Motorola series. We were learning HC11 microcontrollers, so I kind of knew where to go look. And we had manuals for the 68000, a big step up from the 6502. But the other thing, another connection that I learned, because I had one, was a Sega Genesis, a classic 16-bit machine, in the video game world. Once again, the same chip powering two different things that I used in my life. Just another connection to link those things together. Now, around 2000, I believe it was my senior year, we had a course in digital signal processing. And DSP to me was really neat because we could connect mathematics to other things I was interested in. So we learned about digital filters. So you can see a filter structure here on the page. And, well, at the time, I played a lot of guitar. So the guitar, a lot of guitar people are into classic analog stuff. I mean, people love amplifiers from the 60s and 50s, guitars from that era, vacuum tubes. So I kind of knew about filters, played with filters, and then I was learning about digital filters, and that really sparked curiosity. I discovered a product made by a new company, a new startup at the time, Line 6. And Line 6's claim to fame with this little kidney bean was the pod that it could emulate everything about that Marshall amplifier on the left without having to haul a Marshall amplifier to a show. And I can tell you, having hauled amplifiers to a show, you get really tired of doing it. It's not fun. And at the time, you could plug directly into a mixer board. And I acquired one of these devices, and I started doing that with my band. I didn't even carry an amplifier. And for the longest time, people would ask me, "Where's your amp? I love your tone." And I said, I absolutely don't. I bring the pod. Because most people couldn't even tell the difference. There might be some connoisseurs, but I would submit in a double-blind test. Most people simply couldn't tell. Now, like anything else, you take it apart. Another Motorola chip, the DSP 56000 series. We had manuals for this chip once again in the lab, dev boards. And it was one more thing that just opened me up to a new paradigm in programming of signal processing, because it has its own set of challenges as compared to video games. Both needed to do things very fast, but kind of different types of things and different types of optimizations that really made me a better programmer and a better engineer, kind of figuring it out. Now, like all time things in college, if you do things right, you graduate. So my first job was at a company called Cortec Incorporated, and the job was to apply digital signal processing to power electronics technologies for, NASA, Department of Defense, so Navy, Army, Air Force. So this was power electronics. At first, I thought I'd hate it because while I did a lot of analog and we did certainly a lot of MOSFET type circuits in school. I really liked programming and DSP. And I originally thought, you know what, I'm not going to like power electronics. And boy, did I get a lesson. So the first thing I got to play with was a dev board for a TMS 320 as a C6701 digital signal processor. This thing just blew my socks off. Super powerful. It ran at 200 megahertz, I believe, thereabouts. Faster than anything else I'd ever got to play with. Had a variable length instruction word architecture. Just reading through the manual in the assembly language, the opcodes, it blew my mind because I had never seen anything like that. And it turned out I gained a lot of good experience because I had to combine the digital side of things with this analog side in Class D power electronics. Now, that tied me into piezoelectric actuators and a lot of other sensors. And it also was fed by, at the time, in my off time, I wanted to make power amplifiers. I wanted to make the little op amps really big and make my own linear power amplifiers. Well, the power electronics work, in this case, fed directly into what I was doing for a day job. Now, the first lesson, full stack hardware engineering. And I'll summarize it this way. It's really easy to trivialize someone else's work or some other field, subdiscipline, because A, you don't understand it, B, you don't know the nuances, and you think you got to figure it out. I can guarantee you don't. That other discipline may become a real source of growth. In this case, power electronics is related, but I'm going to talk about something later with the craft brew. I made this mistake several times in my career, trivializing something that I should not have been trivializing, because I was able to grow a lot by learning about it. Now, this led me up to the next video game level up. Kind of cue the level up music. A new mountain to climb. So, doing all this research, we were working with Penn State University quite a bit at Cortec. And I was working with grad students and professors, and I said, you know what? I'm doing all this work. I could be getting a graduate degree. I'm doing a lot of the same work. I'm building boards. I'm getting hands-on experience. And that's when I discovered at Penn State had the graduate program in acoustics, the science of sound. Now, it is an engineering program, but it brings in a lot of different people. You have physicists, mechanical engineers, electrical engineers, and then everything else, bio, speech, human hearing, all coming in to this program wanting to learn about how sound waves propagate in water, in air, in materials. And for me, it was a shock. I'd been out of school, in tech school, partial differential equations on day one. This is the acoustic wave equation. But it tied in for me because I thought at the time, mistakenly thinking I wanted to go and work for an audio company, that this was the next thing to unlock me going to Yamaha, Korg, even maybe Line 6, and working on some really cool stuff. But it opened my eyes up to things that I had no idea even existed. So after grad school, I got a job at the Penn State Applied Research Lab doing similar types of work for Department of Defense, the Navy, Army, the Marines. A lot of what ARL does is underwater acoustics. Because they have the program in this Center of Excellence for Underwater Sound, lo and behold, we make a lot of undersea weapons, vehicles, but it also ties in the robotics. And that's where I kind of learned all ground robots are designed after the movie Short Circuit, Johnny Five, still alive. The design really hasn't changed. So I did everything in condition-based maintenance, these underwater vehicles, propulsion systems. I got an opportunity to actually teach part-time EE courses, some basic circuits courses, E310 and 311, amplifiers, circuits, frequency response. 417 was a field program with gate array. There was another project-based course, E4 through W, where we did microcontrollers, projects, those kind of things. And it was really good time. Also still doing work for NXP Semiconductors in a lot of different areas, as well as a lot of consulting over the years. I did some video game type things for the playground industry, as well as some precision timing for circuitry for pyrotechnic industry, which is really cool. So just a wide variety of things that all kind of fit into the sum, of my experiences. But over the years, what I found that I really loved was this focus on connecting embedded systems. So that's taking, the device physics, whether it be through acoustics or some other physical principle, sensors, the firmware, FPGAs. I love all that low-level stuff and putting it all together. Now, on to the meat of what we're here to talk about today is full stack. Now, what do I mean by that? So I'm kind of borrowing that term from the web development world, and a place that I think a lot of people trivialize what some web developers do, but they have a concept of what's called a full stack developer, and it shows up on job ads and whatnot. And I really think the hardware world needs to adopt this. So in the web development world, at kind of like the top level, you have browser technology. You interact with Chrome, Firefox, Internet Explorer, Edge, Opera. And there's technology in there of how those browsers work with HTML5, JavaScript. And then there's web frameworks that at a high level stitch together all these kind of somewhat different technologies, like I said, of HTML, CSS for style sheets, which is extremely powerful now, as well as JavaScript to kind of create this environment. Below those web frameworks are the actual technologies. And we put all that together and call that the front end, because that's the part you see. So when you navigate to a web application delivered over HTTPS, for example, what you see rendered in the browser is considered the front end. And there's actually a lot more than a lot of low-level programmers ever give credit for. It's something that I trivialized until I got into it, and realizing there's actually a lot of technologies here and a lot of neat stuff. Now, it doesn't stop there, because that's just the front end. Well, to serve all this data over the internet, we've got to get it to you. So we need web server software. So things like Apache and Nginx. Another thing, I thought web servers, those are trivial. They give you files. Well, no, they do not. They do a lot more than that. And they can get extremely sophisticated. So how do you deliver all of this content to potentially thousands, tens of thousands, or millions of people? With that comes programming and automation. There's many different programming languages, from PHP to using Python, .NET. You can actually use Perl, C programming to do some of this web automation to run code in the background. All web needs some sort of data store, to store state. You also have to store shopping carts, as well as the state of sensors and all the stuff you need to get to over the internet. And there's a lot of technologies, everything from, we all think of SQL databases, but there's PostgreSQL, Microsoft SQL. There's also other new technologies like for Redis, which is an in-memory data store. But there's a lot of stuff here that someone has to wrap their arms around. And kind of below that is all the infrastructure this runs on. A lot of these servers are run, for example, in Linux on a VM in a big data center or in a Docker container. There's a lot just the infrastructure of running all these services. And so if we group those bottom four, we call that the back end. All the stuff needed to deliver the front end. Well, you can imagine there's actually a lot here, and it's easy to trivialize that this isn't like real programming. It's not low level enough. But I can tell you, after going through this, that to really get good at it and to make a truly awesome product, there's a lot to wrap your arms around. Now, there's people who focus only on front end, only on back end, or even pieces of those. But a person that can kind of navigate that whole system, they call a full stack developer. And it's something that you can put a job ad out for and really gauge of what does that mean. Now, embedded systems, hardware engineering. I like the term full stack engineering to actually apply to this realm as well, because being an engineer is more than making a circuit board. It's more than building the sensor. It's more than just writing the code. So here's where we're going to start. We start at the bottom. Instead of going top down, I'll go bottom up. algebra, calculus, differential equations, discrete math, things you learn in college. You might not use them every day, but there's foundational information and relationships you need to be able to process, engineering, kind of engineering speak. I like to think above that you have higher level logic in spatial processing as well in your brain, as well as understanding geometry, how things interact in space. Because code is kind of like this thing that, where does it exist? Like, it exists in code in this computer. But in hardware engineering, we deal with a lot of spatial things. Circuit board engineering is a very, it is laminated fiberglass with copper. It's geometry. So that's important. Above that, especially in circuit boards, field theory, electricity and magnetism, materials science, chemistry. That stuff can all feed into sensors. You learn about circuits, devices, transistors, MOSFETs, thyristors, power electronics, power distribution, digital logic. There's a lot of pieces here, but we can keep going up. Well, eventually we kind of can build much more complicated things on top of these things. We have embedded microprocessors. Well, anytime you have a microprocessor, you have to write code for it. Above that, you have some sort of tool chain that you have to get your arms around. You got to understand how GCC works, how a linker works, how the assembler works. Above that, you network microprocessors and microcontrollers together. Understanding TCP/IP networks is important. CAN bus, all the things to have things talk to each other, as well as there's got to be algorithms to do all this stuff, as well as programming languages to describe what you want to do. So there's just a stack right there. Now, we have FPGAs, register transfer level logic, simulation. In another kind of time, we have signal processing, metrology and measurement, instrumentation, control theory. Well, then there's another time of you got to learn basic design tools, printed circuit boards, assembly and test, the supply chain that put things on those boards, all of the manufacturing and process control. And you can see here, there's actually many stacks in hardware engineering that you kind of got to get your arms around. Now, what else is missing? And I agree, missing from the full stack developer, from the web technologies, human factors. I mean, we're all humans. We've got to deal with each other. Communication skills is a huge part of that, both verbal and written. I'm going to argue emotional intelligence, and we're going to see why it's so important. One that blows my mind of how bad engineers can be at math is basic accounting and economics. I've seen engineers do crazy mathematics but not understand basic things like a balance sheet, profit, how you calculate these things, what you should charge for a product to make it a business, which is actually basic arithmetic. That's important. Sales and marketing, guys. Guess what? Someone's got to sell the things you're building, and if you're not selling it, you don't have a job. So lesson 2 in full stack hardware engineering, your effectiveness ultimately is limited by how well you can work in a team. That team's going to have much different skill sets. In every person, it's going to have some imperfect interface. The cable going to all your different people on your team, they might talk a little bit different. It's really important to know how you interact with other people. One person can do a lot, but it takes teams to really build truly remarkable things. And I also draw from that the best ideas in the world. I don't care if you invented warp drive for a starship. If you can't communicate that idea effectively and concisely, it's useless. You've got to sell that idea. You've got to get other people to help. That's why all these other things in this stack are super important. We tend, I think, as engineers to think about these are soft skills. I argue these will control how far you can go and what you can really accomplish. Now, for me in life, the next challenge, and this is where we're going to talk about beer, is T0. So who is T0? Well, 2016, united some mechanical engineering, acoustics, and electronics people. We had to get a quick lesson in what full stack really was trying to run a business, because we can build things, but we got to sell something. So what we came up with as our product was a probe for in situ fluid monitoring. Now, we're looking at applications in craft brewing, for beer brewing, but we're also looking at monitoring glycol for big HVAC systems, and this new frontier of synthetic biology, which is really cool, of synthesizing new stuff, whether it be heme for in the Impossible burger, synthetic dairy products for milk, the stuff we're going to need if we want to get humans on Mars someday, or humans in space. We can use things like yeast to synthesize the things we need, because we can't grow a garden, or we can't take a cow to where we need to go. Now, let's take a look at this, our stack for brewing. I promise we're going to get there, and we're going to talk about beer. Now, the beer brewing process has a lot of steps, and we focus in on one step. But it basically starts off with some sort of grain that gets milled, and then you make this thing, I call it beer tea. You get to this process where you boil the grains, and you kind of create this sugar water, is where you kind of start before fermentation. You take this sugar water and you put it in a tank, the beer tea, or what they call the wort, and you add yeast. Now, the yeast is kind of magic. The yeast causes the beer to ferment. It eats the sugars, generates CO2 and CO2 and alcohol, the thing you really want. Now, the challenge with fermentation, it's a biological process. It's hard to manage. So we've got to extract these sugars during the mashing phase from the grains, and we get different types of sugars. We add yeast to this wort, to this beer tea, and then we transfer to a large fermentation vessel. And if it's at the right temperature, we do something called pitch the yeast. You put in these active living creatures. And so when the conditions are right, the yeast will consume the fermentable sugars in this process called, glycosis. So what we get out of that is carbon dioxide, ethyl alcohol, and heat. The yeast are going to keep eating and eating, and when they're all done, they're going to consume the sugars. They'll settle to the bottom of the fermenter. The yeast can be recaptured. The yeast can be recaptured and reused. But there are some challenges. Well, the yeast, they got kind of a small window they really want to be at. Now, there are yeasts that work outside of this window. There are whole companies that come up with new strains of yeast. But there is kind of a general window of 68F to 72F. There are yeasts that you go much hotter and much colder, say for a lager. But there is a temperature that too hot, they die. When they go too cold, fermentation goes really slow. Now, lagers are meant to be fermented really slow, and they can take a long time. Now, additional heat is generated when the sugars are converted, and so usually you need some sort of active cooling. And to do that cooling, you need a glycol loop or something to run fluid through, say, a stainless steel tube. Now, this requires storage of product in a tank. 7 to 14 days maybe for an ale, up to a month for lagers. So at any operation at scale where you're making a lot of beer, and I'm not talking about homebrew, we're talking about hundreds or thousands of gallons, tens of thousands of gallons over time. These tanks are a large capital expense. They take a lot of space, and you've got to manage it. And for a brewery that really needs to move product, the problem with fermentation is it's a source of delay. The only thing you can do is you either try to ferment faster or you add a lot more tanks, which is expensive. So brewers, they need some way of keeping the brew, knowing where it's at. The challenge is these large fermentation vessels are stainless steel. And interaction with the actual product is limited, and you don't necessarily want to do it. So they measure volume, at least in the U.S., in barrels, which is 31 gallons to a barrel. And the brewers will monitor several variables, some of which are time consuming. One measurement brewers use is called specific gravity. And all it is the ratio of the density of your beer to the density of water. And specific gravity comes out of early chemistry and physics because it's really easy to relate things to water. Now to do that, we've got to measure it. Now, they use SG because it's something that changes over time. The density changes as sugars turn into alcohol. And one way you do it is what's called a hydrometer. And you take this apparatus and put it in a column of your fluid and you float this thing. And you look at the little, graticles on there, and you've got to look and come up with a number. And I can guarantee you everyone looking at that is going to give me a different number. You've got to kind of look at the meniscus, and there's nothing precise about this. And you've got to pull beer. It might get contaminated. Now, this is typically done daily if you have a team to do it, so you can monitor it day by day. But imagine a production brewery. You have a lot of stubby pencils, a lot of clipboards, and a lot of people taking measurements. So you react based on time-based measurements or predetermined dates. A lot of big production breweries just do it on time. This results in idle things in the fermenter. Product and time is lost on this. So results aren't consistent. Different people using a hydrometer can get different results. It's an eyeball, and there are digital hydrometers, but even getting that fluid in the oscillating U-tube, just one bubble in there can throw things off enough points. The question is, what if you didn't have to do this? Well, Miller, Coors, and Emerson did a study in 2018 that beer sits in a tank 40 to 50 hours too long. That results in a lot of reduction in productivity. So I said one of the things that the yeast do is they generate all this CO2, and there's quite a bit of circulation. And I have this cartoon of the bubbles going. So in large breweries, this CO2 is captured for other carbonation processes. For smaller breweries, well, they just have a blow-off valve that is fed into a bucket of water, and you watch the bubbles, and that's the precision tech. I've even seen like some brewers put a camera on it so they can see it at home. Some brewers have to drive in the weekends. So the way we attack the problem is that we decided to use acoustics. So we all know that sound moves through water and fluid and gases. It's the reason we can hear. The ocean is a noisy place. Whales and dolphins use sonar themselves to communicate. And we also know that the rate at which sound moves through a fluid is well understood. It's related to some fundamental factors in chemistry and thermodynamics. And in acoustics, we take sound, and we can reduce those and get the speed of sound into kind of two terms: a stiffness term or a springiness term, and a density term. Well, it turns out if we know sound speed and temperature, we can work back to get to that density if the conditions are right. Now, our apparatus that we came up with, we call it the sonic density sensor. It's designed to fit in a 1.5-inch tri-clamp. And a tri-clamp port is a common fitting. It's a compression fitting that are on a lot of these fermentation vessels, making it super easy to install. Everything touching the beer, which is really important, is 304 stainless. The same material they use to make the fermenter. We use an IP68 rated connector, and the probe can be cleaned in place, which is a big deal. Now for us, the principle of operation is pretty simple. Launch a sound wave, hits a reflector, comes back. Now, everything about this process comes down to time. The baseline time of flight measurements we need to come up with is on the order of 50 microseconds. Now, which isn't a big deal to measure for any particular circuit. The challenge is the changes in sound speed, fluid properties, can be very small. Well, how small? We go down to 60 picoseconds of time difference. Pretty small. Now, we need that as like a quanta, because since there's temperature effects and small change in sound speed, we need to have some resolution to pull out what we want. Sound speed is highly dependent on temperature, and so to use this, we have to put in something pretty good. We found about 0.02 C is the magic number, and to get there, we need a precision bath. And it's something that until this is my first project where I really had to get sub 0.1 C. Precision temperature is a lot harder than people think. Now, there's something we get for free with our sensor, which makes monitoring fermentation really awesome. And let me bring down a quick little demonstration. So here we have our probe. I'm sending out a sound wave. I've got this little simulation and it bounces back. We can measure that time. Well, I can start adding some bubbles. And as we send that sound wave, I've kind of treated, instead of a wave or a field, I'm kind of treating these as particles, but we get a scattering effect. And the more bubbles we get, as that thing gets ripping and roaring, the more scattering we get. Now, it turns out we can measure that. As we get that sound wave scattering, we can measure this in our front end. With some signal processing, we can generate some curves to really help the brewer. So for example, here's a sound speed curve. I can show you alcohol production. And the sawtooth features are actually the temperature control system turning off and on throughout primary fermentation. Now, the sound speed is closely linked with temperature, so you have to have a good algorithm to pull it out. Now, our scattering algorithm, we can take all of that scattering and all that interaction and boil it down to a curve like that, and it's pretty easy to see where fermentation starts, it's at its peak, and it stops. We can apply another algorithm and pull out this and get an estimate of specific gravity. With that, a brewer can kind of know what's going on. Now, a sensor by itself is not a complete product. So one thing we found out for this environment, we needed to get data to the cloud. We actually process all of our data in the cloud through all of our algorithms. And we found out cellular in Cat M1 was the best way to do it, because we could send a device that works out of the box and requires no network configuration for the user. It runs parallel to whatever network they have, and they can be taking measurements on day one. We use the power of the cloud to actually process sensor data. We do some data reduction at the front end, and then we send it to the cloud, and from there we do all of our other algorithms for the acoustic scattering models as well as the SG. And the idea is someday we can actually get to AI and predictive algorithms will tell you exactly when the beer is going to be done. So in the end, we wanted something that's super easy to install, unbox, and integrated in minutes. Now, this is important, and the reason I'm showing you this kind of marketing slide is for an engineer, this is really important. You have to be able to draw a simple picture of whatever it is so anyone can understand it. You know, lesson 3, it doesn't matter who it is, you've got to break down what you're doing in a very simple and concise way. Now, at the end of the day, this is what the brewers care about. A digital dashboard, they can see their fermentation activity and all these variables. They don't care about all the other stuff. Now, for a full stack hardware engineer, you do care about the stack, because it starts with underlying math and physics, chemistry, wave equation, speed of sound. Well, the next layer of the stack is sensing and transduction. All right, I have the constitutive equations for your piezoelectric ceramics. Our temperature sensor is semiconductor based. You got to understand how that works, as well as how we interact with that piezo transducer. We need all that embedded hardware tech. We need analog front ends, piezoelectric drives, calibration, precision clock and timing. We need buck and boost converters to generate our voltages, an ARM Cortex-M processor to run it all. We have NOR flash storage and SPI ports. We use an RS-485 port for our networking. We have I2C ports for talking the peripherals. There's packaging, assembly, and all this stuff. Above that, we're not done. There's software. We've got to program in languages like C, use, say, an RTOS. For example, we do all our security to our cloud backend with Wolf SSL, really important, and use a protocol called MQTT. We use an LTE Cat M1 network to transmit the data, and there's all these other software pieces that you have to know about and have context when you're doing your design to be able to do an effective design, to be able to pick these parts out. So at any piece in here in the embedded side, even if you're only dealing with the embedded, you've got to look across these walls to see the other people helping you. You want to make their jobs easier because they're going to be happy and make your job easier. Now, it also doesn't stop there. We've got to do all the cloud computing. We have all the data ingest into our system. We've got to be able to process this data and do all our algorithms. We have to store data in databases. We run everything on Linux servers. We use Laravel and PHP for our backend, Nginx for a web server, PostgreSQL for database. We have some C# code doing some of our algorithms and some Python for stitching things together. So there's a whole other aspect to this. And as a hardware engineer, it is important to look into this world because decisions we make can affect that world and vice versa. And we need all that to get the brewer what they need. Is what they want is the picture of the bubbling tank, and we need the stack to get there. And being a full stack hardware engineer is really understanding these pieces to put them together and understanding that you have tools and partners along the way. We often look at these as suppliers, but there is just as much partners in this journey because you need what they have to make your product work and vice versa. Now, how does one eat an elephant? Well, one bite at a time. Like, you can't do it all at once. You're not going to learn it all at once. Hardware engineering is incremental. We ended up with this really nice probe with this nice M12 connector. All right, we had to go through a lot of probe designs to get there, knowing that we've got to build Rev A to get to Rev B, and we've got to get through all these challenges, and it's okay to mess up. Likewise, the electronics just didn't show up one day inside the probe working. On the left, we had to start with dev boards. We had to start, moving those dev boards into boards we made to get onto microprocessor evaluation kits to actually see does the stupid thing even work. From there, we have to build, things with wires coming off and make our first rev that actually does something and fix all the problems. So you eventually end up with what you see on the right, which is a nicely designed circuit board that can go in, say, I'll bring it out here. We designed it to go into like a nice test fixture, so it's easily testable. We can put all these pieces together. Don't think you can get this on day one. It takes a team, and it's okay to make mistakes along the way. And I wanted to kind of end here is that some of your largest challenges will not be technical. Absolutely will not. I think the technical ones are the easy things to solve. Some of the challenges you're going to face is battling self-doubt. All these continuous challenges are going to make you feel inadequate. Sometimes interactions with other engineers who may seemingly have a figure out me will make you feel adequate. You're going to have to continuously put yourself in positions where you always feel that where you're getting to, that next piece of knowledge is just out of reach. You just can't get there. And if you're in that spot, that's a sweet spot because that means you're growing. If you feel like you have everything figured out and it's easy, something's wrong. Like, stop. Like, nothing should be that easy. But if you're feeling like you're struggling a bit, that's perfectly okay. You need to be able to communicate these thoughts you have and be able to interact with others and outside of your realm of expertise. You've got to work with people that know other things. And this ultimately really will control, how big your sphere is and how far you can go. And you don't need to be on day one to be able to route a DDR4 memory. I'm on tech forums all the time where a hobbyist will say, hey, I'm trying X and Y, I want to do this. And someone says, put a DDR4 memory, you should be able to do that. And then when really what someone just needed was encouraged saying, hey, start with something simple. Let's build from there. Not everyone in the world does DDR4 memory, ever. And it's okay. You'll get there. And I always say, focus on executing really, really well. And that's always better to execute simple things than complicated things that are executed poorly. I've never seen anything that was complicated, executed poorly, that turned out to be a great project. Now, emotional intelligence. A lot of engineers don't like to go here, but it's really the capacity for us to be aware, to control, and express our emotions, and handle interpersonal relationships empathetically and judiciously. And the reason this is important, this touchy-feely stuff is important, just like a circuit, you can't ignore the details of how a circuit works and expect success. If it's a microprocessor, you can't ignore the technical reference manual. All right? We are biochemistry and psychology. You've got to understand how you work. You've got to understand how your colleagues work so you can interact. You know, we're non-ideal components. We've got to work together. And this is not just touchy-feely stuff you learn in college. This is what it takes to be a real engineer, to work in a real world. Now, this leads a lot to this imposter syndrome. I hear about it a lot, and I see it a lot, especially in engineers. And it's this self-doubt where you undervalue what you do, and you think that you're either lucky or there's some other external force. And I always like this cartoon. It's like, what I think I know and what I think everyone else knows, because they're routing DDR4 memory. Jesus, they're doing awesome things. I must not know anything. When the reality is, what you know overlaps nicely with what other people know, and oftentimes you grow together, not kind of separately. And you're always asking these questions. Am I doing enough? Will this hold up? Am I going to get slammed in a design review? Like, am I the best person for this job? So understanding how your brain works and how you feel is very important to being a good engineer. And this, what I'm going to say here is this is applied, and so many other people have said this better than I, but I think it's an important thing to say, is that most people will likely forget things you've said. They'll generally forget what you did. But people always remember how you made them feel. And you'll remember how people made you feel. In my path, I was influenced by a lot of mentors and teachers who made me feel empowered. And they weren't always tech. My English teacher in high school, Mrs. Lewis, she helped set me on a really good path. And this drove me to do, in my desire to kind of continue down this path of empowerment. And so how you feel really is important. So some common traps, all right? Not invented here. Mine will be better. I would do it differently. While sometimes that may be true, it's such a common trap for engineers. It's never good enough. And I like to say, it's polishing the turd, right? You can keep polishing the turd, but you know what? Someday you got to ship the thing. Get it out the door. Your customers will give you feedback. It's okay. Unless you're sending the space shuttle up and people are going to die, it's going to be okay. But even in there, to effectively put the space shuttle in orbit, you've got to be able to reuse other people's work. You can't be reinventing the wheel every time and thinking about how you would do it differently. Other people are capable as well. The other thing I common trap is this sunken cost. We've put so much into this board design, we possibly can't change how we're going to do it. With the idea is like somehow you're going to get all of that back. Well, the reality, in like our little picture with Curious George, you know what? There's a coconut in a tree that might be not quite a climb. Sometimes you got to scrap and start over. That's okay too. Now, for me, crossing the chasm is about understanding the connections. It was going from the NES to the Apple in the 6502. The guitar and amplifier, line 6 pod, having this 56,000 series processor. The SQ2 synthesizer, I played Sega Genesis. They had a 68,000 microprocessor in it. All these things, in being full stack is about peeling back layers of this onion. Eventually you're going to get to the center, and guess what? Once you do, find another onion. Don't, that's being the uncomfortable part of being an engineer. And remember, like, you can take an equation from physics, right? Knowledge, we've got to integrate some effort over time. You've got to be patient. It's not like you're going to go to college and you know everything. It's not like you're going to go to your first job and know everything. You've got to be patient. I think we as humans have the ability to, we're unique. We retain things between generations of offspring. That being said, it's so important to teach what you know. You don't have to be a perfect teacher. You just have to learn how to communicate, and you have to understand how people learn. Your knowledge will only get better by teaching other people what you know. I've had so many opportunities where I had people teach me who may have not even been as skilled as I in, say, a certain domain, but I can still learn something from that person. So you've always got to be a student. I think this is a huge value that people need to have in engineering. Now, that being said, BrewBot's going to sign us off. I always like to put nice artwork on my PCB. There's always room to put something cool on a PCB. BrewBot saying, hey, see you later. Thanks for attending my session. I hope you had a good time. Feel free to ask me questions now. You can reach out to me anytime. Find me on the internet. I'd be more than happy to talk more about the product, what we do, if you're having a challenge. So feel free to reach out and have a good conference.
Hey, Eli. Oh, I think you might be muted, Eli. Yep.
How you doing, Lawrence?
Excellent. Nice to see you again. Thank you so much. Unfortunately, we scheduled this poorly. We're going to be a bit pressed for time, but the good news is for everybody that you will be over on Discord right at 12. Well, actually, you're supposed to be over there now, Eli, but we'll. I do have a couple questions that I picked. You're a man after my own heart, however. I liked you talking about the sort of human elements of things. I was very similar, although I was an Intellivision guy. I'm probably a little older than you are, Eli. I don't know if you remember the Intellivision.
Oh, I did. Oh, yeah.
Okay. So I had an Intellivision, and then I also had a TRS-80.
Oh, yeah.
And I remember vividly the manuals that you talked about, and the book, Learn Basic, and also the tape drive that we bought that had a big electromagnet when you wanted to erase the tape. The cassette tape where you were storing stuff. Those were the good old days, I gotta say. So I connected with your conversation at that point for sure. But I do have a couple of questions. First of all, at what point did you realize that the human/soft skills were important? Because as I said, in my career, I realized that really before I got into business. I always wanted to be in the business element of engineering. But when did you realize that the soft skills were important?
Unfortunately for me, it took a while because I was always really focused on the tech details and
Sure.
Probably, like I mentioned, trivialized some of these other human factors. But once I got into my first real job and then after graduate school, I had a lot of ideas and I was part of a lot of research programs, but I realized someone else was controlling where these things were going, what projects we were pitching for.
Right.
And I had a real problem of communicating, hey, I have this idea, let's go after this customer. And I need to learn how to put this down in a way that we can sell it and explain it, because not everyone has a degree in electrical engineering.
Sure.
And a lot of times those people have the money. And so it's a really good idea to understand how other people think and how you can communicate warp drive or whatever it is
Sure.
you're trying to build.
So that actually leads, that's a great segue to a question that came in. And I asked the questions in this order for a particular reason, Eli, because I think one leads to the other. For me, it comes down to selling an idea, right? It's always about who can sell an idea. And I always like to look at John F. Kennedy selling this concept of, Earth to the moon. In 10 years, right? Clearly you need to be a pretty darn good salesperson in order to get that thing funded. How did you get T0 funded? Now, is that something you did on the side, or were you working while you were doing it? How'd you get that thing off the ground?
Kind of a little bit of both. It did take at one point with my other partners, Steve and Nick Wells, they come from a mechanical engineering and acoustics background as well. But it was us kind of thinking of ideas, putting those ideas kind of on paper with these very simple bullet points, like you said, Earth to the Moon in 10 years,
Yeah,
and not being afraid to put yourself out there and shop it around, and not being so tied to one particular idea, and in not being willing to listen, because for example, your business partner or your investor is a customer as well, being able to listen to what they're interested in and I think that was a huge part of just being out and about and communicating with people, because ideas are plentiful and cheap. Execution can be really hard. So you have to be out there really simplifying and boiling this idea down so you can like increase that sphere and bubble. And some of it is that hard work. Some of it is serendipity, luck,
sure.
being at the right place in the right time. But you can't be at the right place in the right time unless you're out doing it and putting yourself out there.
Sure. Well, so then I'll make this the last question. This one came in, and I think it also segues nicely with what we already discussed, which is, what is the thing, and I think I might know the answer based upon the talk and also the conversation we just had, but what is the one thing you wish you knew when you started that you obviously know now?
That's a hard interview question. It was probably I thought when I got started that I had to know everything and kind of be this expert, and I always felt bad that I didn't understand something, when sometimes, like going back to the communication and being able to communicate ideas, that had I known that was actually more effective and could have probably gotten me further, in realizing that, well, I had these insecurities, guess what? So did everyone else. And that was the magic key of getting over that. And that enabled me to open up and talk to people and realize that they have their own stories, their own insecurities. That was actually a really big deal.
Well, so and I told you, I said this would be the last question, but I want to have the conversation. So unfortunately, we go long. It's usually my fault. Is that something that you invested formally in, or is this something you just sort of developed on the job? In other words, these skills that you had to communicating ideas, selling ideas, empathy for others, those sorts of things. Is that something you read books, or did you just sort of continue to sort of chip away at it?
I think it was a little bit of both. Some of it was taking risks. Like the risk to go to grad school for me was huge, because I had to leave a good job and say, I'm going to be poor again, but I need to make this change, and here's what I got to do. That was huge. Joining groups, like I joined a speaking group called Toastmasters, getting in front of people, just learning how to speak. So there was some of that, as well as just trying to drop the fear of just speaking to people about really what's on your mind, and doing it in a very cordial and respectful way, but just practicing at communicating by doing it. And that to me, I think there's probably more from the school of hard knocks than say of a business, but some of it was just, saying, you know what, let me just do this. And I'll kind of leave it at this. I remember early on in my career, we were meeting another company, and there's this mechanical engineer combined with an artist. He was brilliant, and he was at the milling machine. And I said, you know what, I'd love to be able to learn how to do some of this. He said, Eli, let me tell you something. If you really wanted to, you don't need a book. You'd be doing it. And that had an impact on me, saying, you know what, if I want to do this other thing, even communicating or public speaking, the first step is deciding you want to do it and executing. And that's why it's back to ideas are plentiful and cheap.
Sure.
Execution of anything is really hard.
Well, Eli, I would say that there is no better advice. As I said earlier in the week, I am a proud father of 3 13-year-olds, and and although I've never suffered from being able to come up with words, a lot of the other things I've done in my life, people at the end say, how the heck did you pull that off? I said, well, I just tried it. And I think that's great advice, Eli. And with that, I will send you over to Discord to continue the conversation, and we'll wrap at least the sort of formalities of the conference. We have a couple sessions this afternoon, but with that, Eli, I thank you from the bottom of our hearts here at Altium, and I really enjoyed your talk and look forward to talking with you over at Discord.
Awesome. I really appreciate the opportunity and hope everyone had a good time at Altium Live 2020.
Thank you, Eli.